I want you to close your eyes for a second. Well, unless you were driving, of course.
Right. Please keep your eyes on the road.
Yeah, safety first. But if you can, I want you to think back to your high school chemistry class.
Oh, wow. Okay. Taking us back.
Yeah. You are sitting at one of those, like, heavy black chemical-resistant lab tables.
The ones with the weird stains you can never quite identify.
Exactly. The ones that always smell faintly of sulfur. And sitting right in front of you is one of those classic stick and ball model sets.
Oh, I know the ones.
You probably are picturing the little black plastic spheres for carbon, right? And the slightly smaller white ones for hydrogen.
Yeah, and maybe some red ones for oxygen thrown in there.
Right. And then you have those stiff little gray plastic springs or those wooden pegs that you use to connect them all together.
It is a universally shared memory, honestly. Anyone who has taken a science class in, the last 80 years knows exactly what you're talking about. Yeah. And there's a very specific sensory satisfaction to it, you know?
Oh, absolutely. That tactile click when you push the peg into the hole.
It just feels right.
It is an incredibly comforting image because, it takes this microscopic, invisible, overwhelmingly complex quantum world, and it just makes it tangible.
It scales it up for us.
Right. You snap the pieces together like Lego bricks, and suddenly you have a molecule. You can physically hold it in your palm.
Yeah, but there is a danger in that comfort.
What do you mean?
Well, in that mental model, the atom is a fixed, finished object, right?
Mm-hmm.
It has a set number of holes pre-drilled into it, and the bond is just the physical stick you jam between them.
Right. That's exactly how I picture it.
But what if I told you that this deeply ingrained mental image, like the literal foundation of how we were all taught to draw and understand the physical world, has the causality completely backward?
Backwards.
Completely backward.
Okay, that is a terrifying thought for anyone who spent hours memorizing textbook diagrams.
I know. It is a bit like realizing you have been looking at an optical illusion your entire life, and suddenly the picture flips on you.
Yeah. We are so heavily conditioned by those plastic model kits to think of the universe as a collection of static, finished building blocks that just, happen to bump into each other and stick together.
Like tiny magnets or something.
Right. But that model, as comforting and mechanically satisfying as it is fundamentally a superficial reading of physical reality.
Okay, well, that profound realization is exactly the mission of this deep dive today.
Yes, it is.
Because today we are exploring a massive, truly paradigm-shifting 2026 monograph by Philip Lillian.
It really is a massive shift.
It is. The book is titled Closure Chemistry, Closure Ontology and the Structure of Reality.
Quite a mouthful of a title.
Yeah, it is. Now, I know the phrase structural ontology sounds like we are about to dive into some impenetrable philosophy lecture.
It does sound intimidating, I'll give you that.
But stick with me here. Lillian is proposing something that completely upends our visual and conceptual understanding of matter.
He really is. He argues that molecules are not just Lego aggregations of localized bonds. They aren't a box of prefabricated parts.
No, not at all.
Instead, he defines every molecule in existence as an achieved regime of closure organization.
Right. And what's fascinating here is the sheer scale of the ambition.
Yeah.
Well, to be incredibly clear right up front for the listener, Lillian is not telling quantum physicists that their math is wrong.
Oh, okay. So the math still works.
Absolutely. If you calculate the energy of an electron using quantum mechanics, the numbers are still correct.
Phew. That's good to know.
And he is not telling classical bench chemists that their lab results are invalid either. The equations work. The chemical reactions still happen exactly as they always have.
So then what is he actually doing if he's not saying the old science is wrong?
What he is doing is offering a new structural ontology to explain why chemistry's operational rules actually work in physical space.
The why, not the how.
Exactly. He is providing the missing conceptual layer between the pure, abstract mathematics of quantum physics and the macroscopic physical world of actual chemical reactions.
Okay, let's unpack this because I want to make sure we really ground this for you, the listener.
Yeah, let's bring it down to earth.
We are talking about an aha moment here that will forever change how you look at the physical matter making up the world around you.
It will ruin stick and ball models for you forever, I promise.
Yeah. By the end of this hour, we are going to look at the water in your glass, the rigid plastic composing your computer keyboard, even the DNA spiraling inside your cells through an entirely new lens.
And we are going to do it without drowning in a sea of impenetrable academic jargon, hopefully.
We will do our best, But to get there, before we can even think about building a molecule, we have to completely rethink the building blocks themselves.
This is step one.
Right, we have to shatter the idea of the atom as a static, finished object.
That is the necessary and honestly perhaps the most difficult first step.
Because it's just so ingrained in us.
Exactly. We have to deprogram our brains from what Lillian calls reduction by aggregation.
Reduction by aggregation. Okay, what does that mean in normal English?
Well, it is a view that has dominated scientific thought for well over a century. In the traditional view, you treat a physical structure as though it is entirely exhausted by the local pieces it is composed of.
So, like, a wall is just the sum of its bricks.
Right. You have an atom, it is a discrete finished thing. You add another atom, it is another discrete thing.
And now you have two things glued together.
Yeah. But Lillian argues that treating atoms as finished objects is an ontological dead end. It just doesn't work.
So what's the alternative?
To fix this, we need to introduce his foundational concept, the atomic partial closure spectrum.
Okay, wait. You are losing me right out of the gate here.
Sorry. Let's say?
If the atom's only goal is to eventually form a molecule, why do we call it partial?
That's a great question.
Like, are you saying an atom sitting on its own in a vacuum is somehow broken or incomplete? Because I always thought an atom was structurally sound as long as its protons and electrons were balanced.
Right, that captures part of the traditional thinking. But consider what stability actually means in this new framework.
Okay.
An isolated atom, according to closure chemistry, is neither fully open nor fully closed.
It's somewhere in the middle.
Yes. It exists in a state of what Lillian calls structured incompletion.
Structured incompletion.
Right. It certainly has local stability. I mean, you have a nucleus, you have electron shells, you have a radial stratification. The atom is not just falling apart.
It's holding its shape.
Exactly. However, it possesses these restless, symmetry-resolved channels that are essentially searching for relational stabilization.
Restless channels.
Yeah, they have a latent directionality. So the atom has this repertoire of available modes that are highly organized, but they remain structurally unresolved until it meets a partner.
So instead of thinking of atoms as hard Lego bricks with fixed permanent pegs waiting to snap together, they were more like, I don't know, malleable puzzle pieces.
Well, I like it.
But like puzzle pieces that are actively, restlessly seeking to resolve this open state.
Yes, exactly.
It almost sounds like a kind of structural tension. Like the atom is stable enough to exist, but it is deeply unsatisfied.
That's a perfect way to put it. It is unsatisfied. It is carrying around this potential energy, this relational availability.
Okay, I think I'm picturing it now.
And if we connect this to the bigger picture, you can actually see this tension clearly by looking at the extreme edge cases in the periodic table.
The edge cases.
Yeah, let's look at the noble gases. You know, helium, neon, argon.
The ones all the way on the right side of the chart.
Right. Lillian defines the noble gases as representing the noble gas limit.
The limit of what?
They are the closest thing in ordinary, everyday chemistry to near-complete atomic closure.
Oh. Because they don't want to react with anything.
Precisely. Their local internal organization is so saturated, so perfectly resolved within the boundaries of the single atom, that the drive for outward relational bonding is massively suppressed.
They're just happy by themselves.
Yeah, they simply do not have that restless spectrum of unresolved partial closure modes like the other elements do.
Wow. Okay, which explains so much.
Doesn't it?
If you were walking down the street and you see a glowing neon sign, that neon gas is just trapped in a glass tube and the atoms are just floating around, completely ignoring each other.
Bumping into the glass, bumping into each other, but never sticking.
Right. They don't bond. They're already closed. They've achieved their perfect state.
Exactly.
But everything else, the carbon in the sandwich you ate for lunch, the oxygen you're breathing in right now, the nitrogen, they are existing in this constant restless state of partial closure.
Yes. The vast majority of the periodic table is existing in structured incompletion.
Okay, so this brings up the most obvious question. What happens at the exact moment two of these restless, partially closed atoms actually meet?
Ah, yes.
Because if we are throwing out the Lego model, they don't just mechanically collide and click into place.
No clicking.
It sounds much more fluid. It sounds almost like a negotiation.
Negotiation is actually an excellent framework for what happens next.
Oh, good.
Because when two or more atomic centers are brought into proximity, they enter into a shared relational constraint.
Okay, so they have to deal with each other.
Right. Their isolated, individual, partial closure spectra can no longer exist independently. They are forced to adapt to the presence of the other atom.
So they compromise.
In a way, yes. The atoms must reorganize their available restless modes into mutually compatible, stabilized channels.
Wow.
Lillian formalizes this as entering molecular boundary conditions, and the resulting reorganization is called closure adaptation.
Closure adaptation.
Yes, the atoms produce what he calls bond-adapted closure channels.
So, to be incredibly literal here,
Let's do it.
the bond isn't a stick. It isn't a physical rod holding two spheres apart.
Absolutely not.
And it isn't just a pair of dots shared between two letters on a chalkboard, like we drew in high school.
It is neither a stick nor a pair of dots.
So what is it physically?
A bond is a stabilized relational channel through which closure is jointly distributed between the participants.
A stabilized relational channel.
Yeah. It is the physical, spatial manifestation of that successful negotiation we just talked about.
Okay.
The atoms are actively adapting their internal symmetry to find a mutually agreeable state of rest within a shared boundary.
Well, here's where it gets really interesting, I think.
Oh, we're just getting started?
To really grasp how this negotiation works, how they reach this agreement, we need to look at the mathematical heart of Lillian's theory.
Yes, we do.
Now, listener, do not panic.
Yeah, stay with us here.
We promise to keep the dense jargon to a minimum, and you do not need a PhD in calculus to understand what this equation is doing.
It is conceptually very elegant.
So Lillian introduces something called the closure admissibility functional. Let's just call it the FCL for short.
CL, right.
The way I am reading this, it is essentially a cosmic accounting ledger for the molecule, right?
Thinking of it as an accounting ledger is a highly, highly functional analogy. I like that a lot.
Because it weighs pros and cons.
Exactly. The admissibility functional calculates whether a proposed molecular organization can actually exist in physical reality.
Right.
It weighs the gains of a potential geometric arrangement against the penalties.
Yeah.
It is a strict balance sheet.
Okay, so let's look at the sheet. What's on the gain side of the ledger?
On the gain side, you have scaffold formation.
Which is what?
This is the creation of the primary relational links, the core architecture of the molecule.
Okay, so just making the connection gets you points.
Yes. You also gain points for angular balance.
Angular balance.
How well the various closure channels can separate from each other in three-dimensional space without, impinging on one another.
Keeping their distance.
Right. And finally, you have coherence. The stable, seamless overlap of these relational fields.
Okay, so if I am a carbon atom trying to negotiate with some hydrogen atoms, my goal is to maximize my scaffold, keep everyone perfectly spaced out, and maintain coherence. That puts me in the black.
That is a very profitable negotiation, yes.
But what about the penalty side? What makes this cosmic ledger go into the red?
The penalties are entirely based on unresolved spatial and structural tension.
Okay.
For example, you are penalized heavily for closure crowding.
Closure crowding, just literally getting too cramped.
Yes. This is what happens when too many adapted channels are forced into the same geometric sector of space. The channels begin to physically interfere with each other.
That makes sense. What else?
You also have structural strain, which is the energetic cost of forcing a molecule out of its ideal, mathematically perfect angular balance.
Bending it out of shape.
Right. And finally, you have nonbonding localization, which essentially involves closure capacity that doesn't get shared with a partner and instead hoards local space.
Oh, we will definitely explore that one in detail shortly.
We will. It's crucial.
Yeah.
But the core rule of the ledger is this. A molecule is only stable, it only becomes a physical reality, if the gains of this negotiated geometric arrangement sufficiently outweigh the penalties.
Okay, I want to push back on something here, or at least ask for a real-world example.
Sure, go ahead.
Give me an example of the ledger going into the red.
Okay.
What does structural strain actually look like in the real world? Because if molecules are just these invisible math problems solving themselves, what happens when the math is bad?
This raises a really important question, and it has very dramatic real-world consequences.
Okay, what is it?
Let's look at a molecule called cyclopropane.
Cyclopropane.
Yes. It is made of 3 carbon atoms arranged in a ring. A perfect triangle.
Okay, 3 carbons, triangle shape.
Got it. Now, the ideal mathematically perfect angle for carbon bonds in that specific state is 109.5 degrees.
109.
But a physical geometric triangle requires internal angles of exactly 60 degrees.
Oh, wow.
Yeah.
So you are taking something that desperately wants to spread out to roughly 110 degrees, and you are physically bending it, crushing it down into a 60-degree corner.
Yes. The structural strain penalty on the FCL ledger is astronomical.
It's severely in the red.
The negotiation was incredibly difficult, the boundary conditions are highly punitive, and the resulting closure regime is, frankly, furious.
Furious. I love that.
Sure.
So in the real world, what does a furious molecule mean?
It means cyclopropane is highly reactive, highly unstable, and as a gas, it is highly explosive.
Oh,
It is constantly looking for the slightest energetic excuse to snap that triangle open, relieve the strain, and find a more favorable closure arrangement.
so the ledger directly dictates the physical behavior of the gas in a laboratory.
Absolutely.
That makes so much sense. The molecule isn't just unstable because a textbook says so. It is unstable because it is geometrically tortured.
It is failing the admissibility audit.
Failing the audit. That's a great way to put it.
Yeah.
But, if a molecule is just a solved spatial negotiation, if it is just a balance of this ledger, this brings up a really weird philosophical question for me.
Lay it on me.
Do atoms lose their individual identity once they bond?
Oh, that is a huge debate.
Right. Because if they're adapting and fundamentally reorganizing their internal structures to form this new shared reality, is the carbon inside that strained cyclopropane triangle still carbon in the way we traditionally think of it?
Standard chemistry actually struggles deeply with this exact question.
Really?
Yeah, pedagogically, we oscillate wildly between two extremes.
What are the extremes?
Sometimes we treat atoms in a molecule as perfectly unchanged, isolated spheres that are just, holding hands.
The Lego bricks again?
Exactly. But other times, in advanced quantum molecular orbital theory, we treat the molecule as a completely new, holistic, smeared-out blur.
The blur.
Yeah, where the individual atoms have seemingly vanished into this global electron cloud.
So they lose their identity entirely.
In that model, yes. But Lillian's framework masterfully avoids both of these extremes.
How does he split the difference?
He states that atomic centers persist as local closure poles within a more extensive molecular closure field.
Local closure poles. Okay, I am trying to visualize that.
It takes a second.
So it is like an actor taking on a role in a play.
Okay, I'm following.
The actor, let's say Tom Hanks, is still fundamentally Tom Hanks. He maintains his identity.
Right.
But his behavior, his posture, his emotional interactions, all of that is completely dictated by the script, the context of the scene, and the other actors on the stage with him.
That's a fun way to look at it.
So the carbon atom in methane is playing a very different role than the carbon atom in carbon dioxide, even though the core actor is exactly the same.
That captures the essence of it, but let's refine it slightly to make it physically accurate.
Okay, refine away.
Imagine the actor doesn't just change their posture, but the actual physical tension in their muscles and the space they take up on stage morphs based on who stands next to them.
Oh, wow. That's a visceral image.
The atom maintains its core identity. The carbon nucleus remains a recognizable pole of organization. But its realization, the actual physical geometry of its channels, is entirely dependent on the shared boundary conditions of the whole molecule.
So the carbon atom persists, but its structural expression is radically transformed by the negotiation.
Precisely.
Okay, this dependency on context, this shared boundary condition, leads us directly to what I think is Lillian's most controversial move.
Yes. The great reversal.
The outline calls it the great reversal. We understand that atoms negotiate space, and they consult the ledger.
Right.
But now we have to look at the physical 3D shapes they actually take. And this is where closure chemistry takes a sledgehammer to traditional textbook pedagogy.
Yes, this is the paradigm shift that will require the absolute most unlearning for anyone trained in 20th century chemistry.
Let's talk about those textbooks, because honestly, I am feeling a little betrayed by my AP chemistry teacher right now.
They were just teaching what they knew.
I know. But if you took chemistry, you spent weeks learning about something called hybridization.
The dreaded hybridization.
You learned that a carbon atom has different types of, parking garages for its electrons. One's orbital, which is shaped like a sphere, and 3 p orbitals, which are shaped like dumbbells.
Yes, the classic shapes.
And the textbook tells you that when carbon wants to bond to, say, 4 hydrogen atoms to make methane, It takes these different distinct orbitals, throws them into a quantum blender, mixes them all up, and pours out four perfectly identical hybrid orbitals called ST3.
And standard doctrine dictates the causal arrow of that process very strictly.
Right. The doctrine says, because the atom mixed its orbitals to create four identical sp3 hybrids, the molecule is forced to take on a tetrahedral shape.
Yes.
The mixing of the invisible quantum orbitals causes the physical geometry of the molecule. I spent hours memorizing that rule for a test. Are you telling me that's wrong?
I am telling you that according to closure chemistry, the causal arrow is pointing in the exact wrong direction.
The wrong direction.
In Lillian's framework, the spatial geometry is the primary physical reality.
The geometry comes first.
Yes. The geometry is not a byproduct. It is the fundamental solution to that admissibility functional we just discussed.
The ledger.
Right. It is the most stable, least penalized way to distribute the closure channels in three-dimensional space based on the boundary conditions.
So what does this all mean for the sp3 hybridization rule?
It changes its status completely.
Are you saying hybridization is like drawing property lines on a map after the tectonic plates have already settled into continents?
That's a phenomenal conceptual bridge.
Because the map describes the terrain perfectly, but the lines on the map didn't create the mountains.
Yes, exactly. In Lillian's ontology, hybridization is what he calls a derived representation.
A derived representation.
It is a post hoc labeling system. Chemists invented the concept of sp3 hybridization to mathematically describe the geometric reality that has already physically stabilized. The absolute equivalence of the four bonds in a methane molecule isn't the result of a magical, invisible, orbital blending rule happening behind the scenes.
It's not the blender.
No, it is simply the natural, inevitable result of symmetric closure resolution.
Wait, let me make sure I have this exactly right.
Take your time.
If you have a central carbon atom and you have four identical hydrogen atoms pulling on it, demanding a negotiation,
Right.
the absolute most efficient, least crowded way to resolve that spatial negotiation in a 3D universe is just a perfect tetrahedron.
Precisely. The geometry is the answer to the special problem.
And this P3 label.
This P3 label is just the name tag we slap on the answer afterwards so we can do math with it.
But doesn't this throw out 100 years of quantum mechanics?
People always ask that.
Are we saying Linus Pauling and all the founders of quantum chemistry were just making things up?
Not at all. And Lillian is meticulously careful here.
Okay, how does he thread that needle?
This is why distinguishing between a state description and a structural ontology is vital. Lillian isn't calling quantum orbital theory false.
He isn't.
No. The mathematical models of hybrid orbitals are incredibly, astonishingly accurate for predicting energy states and doing complex calculations. They are a perfectly valid state description.
Okay, so the math works.
But closure chemistry provides the actual structural ontology. It tells us what is physically, structurally happening in reality.
So what's actually happening?
The spherical and dumbbell orbitals don't physically blend like paint in a bucket. Rather, the atomic partial closure modes reorganize into a globally symmetric geometry because the molecular boundary conditions absolutely demand it. The geometry comes first.
Okay, I am taking a deep breath here.
It's a lot to take in.
It's a massive shift in perspective.
Right.
We are moving from a universe of prefabricated parts following invisible mathematical rules to a universe of dynamic, negotiated relationships solving spatial problems in real time.
It feels much more alive, doesn't it?
It really does. But to prove this isn't just abstract armchair philosophy, we need to apply this geometry-first rule to real, tangible molecules.
We do. We need to ground it.
We need to look at what Lillian calls the taxonomy of regimes.
This is where the theoretical elegance of closure chemistry truly shines. We can map the entire molecular world based on how these spatial negotiations are resolved.
I love a good map.
Let's start with the simplest, most perfect resolution. Let's look at regime 1, primary scaffold closure.
And for this, we are bringing back our poster child, methane. CH4, 1 carbon, 4 hydrogens.
Correct. We just established that carbon brings its partial closure spectrum to a negotiation with 4 equivalent hydrogen atoms.
Right, and the FTL ledger says, to maximize our gains and avoid the terrible penalty of closure crowding, we need to spread these 4 negotiated channels as far apart from each other as physically possible.
Exactly. 4 equivalent outward channels naturally seek maximum spatial separation.
Okay, if I am a listener trying to visualize this,
Let's give them an image.
imagine taking 4 balloons, tying them all together at the knot, and letting them push against each other.
That's a classic chemistry teacher demonstration.
They will automatically arrange themselves into a perfect tetrahedral shape. It looks like a caltrop, or maybe a camera tripod with a camera pointing straight up.
Yes. In three-dimensional space, the absolute mathematically optimal solution to separate 4 points around a center is a tetrahedron.
With angles of exactly 109.5 degrees.
It is perfectly symmetrical. It is the baseline of perfection.
Wow.
In this regime, the primary scaffold itself is the complete closure success. There are no leftover parts. There are no unresolved tensions.
It's a clean ledger.
Very clean. The entire closure capacity of the carbon atom is cleanly, beautifully distributed into the 4 shared relational channels with the hydrogens.
Okay, so methane is the shining example of perfect spatial harmony.
It really is.
But the universe is rarely perfect.
Rarely.
What happens when things get a little awkward?
Awkward is a good word for it. Let's move to regime 2, concentrated non-bonding closure.
And for this, we are looking at ammonia, which is NH3, and water, H2O.
Right.
Now, in classical chemistry, we are taught these molecules are basically tetrahedral too, but with these mysterious lone pairs of electrons acting like invisible ghosts that haunt the molecule and push the visible bonds closer together.
And classical chemistry genuinely struggles to explain exactly what those lone pairs are, ontologically speaking.
Because they just draw them as 2 little dots floating in space.
Exactly. They're often treated as just empty space or unshared dots or unused electrons floating around like debris.
Debris.
But Lillian redefines them entirely, giving them massive structural importance. In closure chemistry, a lone pair is not an absence. It is a non-bonding closure concentration.
So wait, if carbon brings 4 hydrogens to the party and gets a perfect tetrahedron, nitrogen in ammonia only brings 3 hydrogens.
Right.
Are you saying the nitrogen molecule still builds the 4-part tetrahedral scaffold, but just leaves 1 slot empty?
It doesn't leave it empty. That is the crucial
Well,
distinction.
it's not empty.
The 4th channel doesn't just vanish into the ether. Because nitrogen's atomic boundary conditions demand a 4-channel resolution, that 4th channel becomes occupied by this non-bonding closure concentration.
So it's filled with something.
It is a very real, very dense presence of closure capacity that simply didn't find an external partner to share the load with.
Okay.
And here is the critical structural insight. Because this concentration does not extend outward into a shared relational space with another atom, it remains highly localized.
Localized.
It is trapped close to the nitrogen nucleus.
Okay, I have an analogy for this. Tell me if I'm on the right track.
Let's hear it.
So a lone pair isn't just an empty seat at a table.
No.
It's like a passenger on a crowded subway train who aggressively hogs the armrests and manspreads.
Oh, I like this.
Right. They aren't holding hands with anyone. They aren't connecting with the person next to them. They are just taking up a massive amount of personal space.
Exactly.
And they are forcing everyone else on the bench to physically squeeze together to maintain harmony in the train car.
Let's build on that, because mechanically, that is exactly what is happening.
Really?
Yeah. Imagine that man-spreading passenger is also emitting a localized magnetic field that physically repels the people sitting next to them.
Oh man, the worst kind of passenger.
Truly. It is not just passively taking up space, it is actively exerting localized pressure. Lillian calls this specific phenomenon closure crowding.
Closure crowding.
That localized non-bonding channel intensely hoards the local angular capacity around the nucleus.
So it's pushing the hydrogens out of the way.
Yes, it exerts severe closure pressure on the 3 shared bonding channels, physically forcing them to compress together to balance the overall admissibility functional.
The ledger demands compromise.
The ledger always demands compromise.
That is why the bond angles in ammonia get crushed down.
Exactly.
They go from the perfect, harmonious 109.5 degrees we saw in methane down to 107 degrees. The man-spreading lone pair is taking up too much room, so the hydrogens have to squeeze closer together.
Yes. And if we extend this logic to water, H2O, the situation becomes even more extreme.
Why is water more extreme?
Because the oxygen atom in water only has 2 hydrogen partners, but it still operates within a 4-channel underlying architecture. So you have 2 of these non-bonding closure concentrations. You have 2 passengers man-spreading on the train.
Oh, wow. So the localized closure pressure is doubled.
Exactly.
Yeah.
The pressure is significantly greater, and the 2 hydrogen bonds are forced even closer together, compressing the angle down to 104.5 degrees.
That is brilliant, and it is so viscerally easy to picture.
It's a very intuitive model once you get the hang of it.
It really is. It takes the old via separa theory we learned in school valence shell-electron pair repulsion.
The bane of many chemistry students.
Totally. Which always felt a bit like a clunky rule of thumb we just had to memorize for a test.
Mm-hmm.
And it absorbs it into a much more unified logical framework.
Right.
It isn't just negatively charged electrons blindly repelling each other. It is the entire spatial field of the molecule, dynamically rebalancing its closure capacity to minimize penalties on the ledger.
It absorbs the heuristic into a true structural ontology. It finally explains the why, not just the what.
Yeah, that's the key.
And I want to emphasize how important this is for the listener's daily life.
How so?
That compression down to 104.5 degrees in water, that bent V-shaped geometry is the only reason water is a polar molecule.
Because it's bent.
Yes. It is the reason water molecules stick together, the reason ice floats, the reason water is a universal solvent.
Oh my God.
If water were perfectly linear, life on Earth would not exist. That man-spreading lone pair is responsible for biology.
That is mind-blowing. The geometry is everything.
It really is.
So we've seen what happens when the four channels are perfectly balanced, and we've seen what happens when they are hoarded by lone pairs.
Right.
But this logic has to scale.
It scales all the way up.
What happens when a molecule's primary skeleton only needs 3 channels to begin with, or 2? What happens to the leftover capacity when the subway train is mostly empty?
That is a great transition. This brings us to taxonomy part 2, layered closure and unsaturation.
Okay, layered closure. Let's look at regime 3. Localized residual closure.
This is where we encounter the infamous double and triple bonds.
Right. In standard high school chemistry, if carbon bonds to another carbon and only has 2 hydrogens to share, like an ethene gas, C2H4, you just draw 2 parallel lines between the carbons on your paper, you memorize the label BINSPIO, you learn the shape is flat, and you move on.
Yeah, it's just treated as bond 2.0, a single bond but upgraded.
Like a thicker stick.
Exactly. But Lillian is saying a double bond is not just a thicker, stronger version of a single bond. It is fundamentally ontologically different.
How so?
In closure chemistry, we do not just draw an extra line. We look at the primary scaffold first as a foundational layer.
Okay, the foundation.
Under the boundary conditions of ethene, the carbon atoms negotiate a planar 3-channel primary scaffold.
Let me build this in the theater of the mind for the listener.
Please do.
Imagine taking 3 wooden dowels and laying them completely flat on a table, radiating out from a central point like a peace sign.
Great image.
They resolve the majority of the closure demand in a flat trigonal shape with perfect 120-degree angles. Everything is totally flat on the table.
That is the primary scaffold. But here's the problem. The carbon atom still has leftover closure capacity.
Oh, because it usually wants 4.
Exactly.
Well,
It has an unresolved mode. Lillian defines this leftover unassigned capacity as a residual transverse mode.
okay, so it built the flat foundation first, but it still has building materials left over.
Right.
Where does it put them if the table is already occupied?
Because the primary scaffold is strictly flat, the only spatially admissible way to stabilize this leftover capacity without violating the geometry of the flat scaffold and ruining the ledger is to build a secondary closure layer directly on top of and underneath the planar scaffold.
On top and underneath.
Yes, it is a transverse stabilization. It projects out of the plane.
Okay.
This is what we traditionally call the pi bond in quantum chemistry. But Lillian's framing of layered closure explains its physical macroscopic properties much more elegantly.
Wait, I want to make sure I'm visualizing this right.
Go ahead.
A double bond isn't just a stronger bridge connecting 2 atoms. It's an entirely different type of spatial resolution laid over the first one.
Yes.
It's like building a solid, flat concrete bridge across a river, and then because you have extra steel left over, you build a suspension cable arching over and under the bridge.
That is an incredibly powerful analogy. I'm stealing that.
Steal away.
And consider the physical implications of that suspension cable. What happens if you try to twist the bridge?
Well, if it's just a single straight concrete pillar, a single bond, you could theoretically spin the 2 sides independently without breaking anything, like a wheel on an axle.
Right, free rotation.
But if you have that suspension cable anchored to the top and bottom of both sides, if you twist the bridge, the cable snaps.
And that is precisely why double bonds are rigid.
Oh.
If you try to twist a molecule around a single bond, it rotates freely because the primary closure channel is axially symmetric.
Right.
But if you try to twist a double bond, you are literally tearing apart that secondary transverse closure layer.
The suspension cable.
This suspension cable, as you put it, relies on the strict, unyielding directional compatibility of the two carbon atoms remaining perfectly flat and aligned.
That makes total sense.
If you twist them, you destroy the admissibility of the residual mode, the ledger crashes, and the bond breaks.
This has huge implications.
It dictates the shape of organic chemistry.
I was reading recently about how human vision works.
Oh, this is a great example.
When a photon of light hits your retina, it strikes a molecule called retinal, and the energy from that single photon is just enough to momentarily break that suspension cable, the double bond.
Right, it gives it just enough energy to overcome the barrier.
It allows the molecule to twist just for a fraction of a second before snapping back. And that physical twist is what sends the electrical signal to your brain that says, "I see light."
That is a brilliant real-world application. The entire mechanics of human sight rely on the rigid, layered closure of a double bond being momentarily disrupted.
It is wild to think about. And does this layered closure logic apply to triple bonds too? Like in ethane gas, C2H2?
Oh, it applies even more intensely.
Really? How so?
In ethane, the boundary conditions dictate a highly concentrated two-channel primary scaffold.
2 channels.
It is essentially a straight line, carbon bonded to carbon with one hydrogen on each end, a completely linear foundation.
So if the foundation is just a single straight line, that leaves a lot of leftover building material.
Exactly. This linear geometry leaves two residual transverse modes available.
2 suspension cables.
These leftover capacities must stabilize, and they do so as two orthogonal secondary layers.
Orthogonal meaning at right angles?
Yes. Returning to your analogy, picture the linear concrete bridge, but now you have one suspension cable running top to bottom and a completely separate suspension cable running side to side wrapped around the central bridge.
So it's incredibly dense. It's fortified from all sides.
It is the absolute maximum concentration of localized closure pressure achievable in standard organic chemistry.
Wow.
And that is exactly why triple bonds are shorter, vastly stronger, and more physically unyielding than single or double bonds.
They're just locked in.
Completely locked in. Lillian's framework doesn't just blindly predict the geometry. It provides a rational, structural explanation for the macroscopic physical properties of the molecule.
Based entirely on how the closure capacity is layered.
Yes, based entirely on how closure capacity is layered and concentrated in 3D space.
It is so satisfying to see all these disparate, clunky rules from high school chemistry class.
Like hybridization lone pairs.
Exactly. Hybridization, VSEPR lone pairs, pi bonds, the rigidity of molecules, all collapsing into this single, elegant idea of spatial negotiation and closure capacity.
It's a grand unifying theory of structure.
It feels like someone finally gave us the master key.
But Lillian doesn't stop with double and triple bonds.
He doesn't.
No, he takes this concept of leftover residual closure and applies it to what has to be the ultimate boss level of structural chemistry.
Oh boy.
We have to talk about benzene.
Benzene. C6H6.
If you want to understand the limits of classical chemistry, you look at benzene.
This is where classical structural diagrams notoriously break down, right?
Yes, and where closure chemistry truly proves its explanatory power, we are entering regime 4, distributed cyclic secondary closure.
Okay, let's give the listeners some historical context here, because the story of benzene is wild.
It's one of my favorite stories in the history of science.
Benzene is a ring of 6 carbon atoms, each attached to one hydrogen atom. Michael Faraday first isolated it in 1825 from the oily residue left over from illuminating gas used in street lamps.
Right, London street lamps.
And for decades, the greatest chemists in the world completely lost their minds trying to figure out how to draw its structure.
Yes, the problem was a mathematical one based on the rules they understood at the time.
Because of the leftover capacity.
Exactly. If you arrange 6 carbons in a hexagon, and each only has one hydrogen, you have a massive amount of leftover bonding capacity.
Right. And the most famous breakthrough allegedly came to a chemist named August Kekulé in 1865.
The famous dream.
The legend goes he was daydreaming by a fire, and he saw a vision of a snake eating its own tail.
An Ouroboros.
Right. He woke up and realized benzene was a ring. But to make the math work on paper, he had to draw alternating double and single bonds all the way around the hexagon. Double, single, double, single.
The famous Kekulé structures.
Right.
But as elegant as the snake eating its tail story is, there was a glaring fatal flaw with that drawing.
The lopsided hexagon problem.
Precisely. If we just discussed how double bonds are shorter, stronger, and tighter than single bonds,
The suspension cable's pulling things tight.
right, then a ring with 3 double bonds and 3 single bonds should not be a perfect symmetrical shape.
It should be warped.
The sides with double bonds should be pulled tighter. The ring should be lopsided, sort of a stretched out hexagon.
But it isn't.
No. Decades of experimental evidence, eventually confirmed definitively by X-ray crystallography, proved unequivocally that benzene is a perfectly symmetrical hexagon.
Perfect symmetry.
All 6 carbon bonds are exactly the same length. They are longer than a double bond, but shorter than a single bond.
So how did standard chemistry explain that glaring contradiction for the last century?
They use a concept called resonance.
Resonance.
Yeah.
Textbooks tell you to imagine the molecule as shape-shifting.
Yes, rapidly.
It is vibrating back and forth between the two possible alternating structures, shifting the double bonds one position over, back and forth, so incredibly fast that the physical bonds just blur into an average.
A 1.5 bond.
Yeah, exactly. And Lillian points out that this is an ontological nightmare.
It really is. The molecule is not actually shape-shifting.
It isn't.
No, it is not vibrating back and forth between 2 fictional lopsided states.
So what is it doing?
The concept of aromaticity, which is the term chemists use to describe the special, almost magical stability that benzene and similar rings possess, is not some mystical heuristic rule.
Okay.
Lillian redefines it simply and beautifully as cyclic closure success.
Cyclic closure success. Okay, let's slow down and unpack this.
Let's do it.
When the textbook shows benzene vibrating back and forth and tells students it's a blur, Lillian is saying the molecule isn't doing that at all. It's perfectly still.
Yes.
It's just that our pen and paper language is completely broken when trying to draw it.
That captures part of it, but let's consider why the language is broken.
Why is it broken?
This is Lillian's concept of projection insufficiency.
Projection insufficiency.
Think about map makers trying to draw a flat map of the spherical Earth.
Okay, sure.
If you use a Mercator projection, Greenland looks the size of Africa.
Right, it's totally distorted at the poles.
It is a distortion caused by trying to project a higher dimensional reality onto a lower dimensional format. Our classical chemical notation drawing straight, localized lines between the letters C and H on a flat piece of paper is fundamentally a localized 2D language.
It's the Mercator projection of chemistry.
Exactly. It is strictly designed to show a specific relationship between atom A and atom B. But the physical reality of benzene is distributed.
Okay, the suspension cable isn't connecting just 2 pillars.
Exactly. Let's build the molecule using Lillian's framework instead of Kekulé's.
Let's do it.
The 6 carbon atoms form their primary planar scaffold, the flat hexagon.
6 pillars in a circle.
They all have one residual transverse mode left over, pointing above and below the plane.
The leftover capacity.
Right. But instead of awkwardly pairing up into 3 isolated, localized double bonds like the old drawings forced them to, those residual modes recognize that they are arranged in a perfect, compatible, contiguous cycle.
They see each other.
Because the boundary conditions allow it, they achieve a global ring-level organization.
Global organization.
The closure capacity is not localized between pairs. It circulates globally around the entire ring scaffold.
So the suspension cable is essentially a continuous floating halo over the entire stadium.
That is a beautiful image and highly accurate.
A halo.
Lillian calls this structural reality closure equalization.
Closure equalization.
The global ring-level organization supersedes any localized edge distinctions. The carbon bonds become structurally equivalent not because they are averaging out a rapid, frantic oscillation between fictional states,
Right, not blur.
but because the secondary closure is genuinely, statically, and peacefully distributed across the whole system.
Wow.
Resonance isn't a physical oscillation of the molecule. It's a symptom of our localized 2D language failing to capture a higher-order distributed closure state.
That is a profound paradigm shift.
It solves a 100-year-old headache.
We literally invented a ghost, this vibrating, rapidly shape-shifting molecule, just to compensate for the fact that our pencils can only draw straight lines between 2 distinct points.
We let our tools limit our imagination.
We let the limitations of our drawing tools dictate our understanding of reality. Lillian is saying, stop trying to draw localized lines, step back and look at the global reality.
Right.
The molecule found a global solution to its closure problem, and that solution is a halo.
And this global solution provides exceptional, unprecedented stability to the molecule.
Because it's perfectly balanced.
Yes. Cyclic closure success lowers the overall penalties in the admissibility functional more efficiently than localized bonds ever could.
The ledger loves the halo.
The ledger is very happy. Benzene is the ultimate, undeniable proof that a molecule is an achieved regime of closure of the whole, not just a blind aggregation of its individual parts.
This all sounds incredibly majestic, honestly.
Doesn't it?
But it raises a really practical question.
Okay, what's that?
If these molecules are these perfectly balanced, beautifully negotiated, harmoniously resolved regimes of closure, how do they ever do anything?
Reactivity.
Right. How does chemistry actually happen? I mean, if benzene has achieved this perfect, untouchable global halo of stability, why would it ever react? Why would it ever change into something else?
That leads us to the final major conceptual shift in Lillian's monograph. The complete redefinition of chemical reactivity.
Redefining reactions now too, huh?
We have to.
Yep.
In classical operational terms, a reaction is viewed as a mechanical attack.
An attack.
Yeah, electrons from molecule A attack molecule B over here, a bond violently breaks over there, atoms shuffle around.
Sounds like a battlefield.
It's very violent language. Lillian reframes this entire process as closure navigation.
Closure navigation, it sounds a lot more peaceful. It almost sounds like plotting a course through a star system.
It is essentially plotting an energetic course through closure path space.
Okay, what does that mean?
A reaction is a structured, logical path moving from one stabilized organization of closure to another.
Moving from one stable state to a new stable state.
Right. Molecules do not just randomly fall apart and blindly reassemble. As they encounter other molecules and their boundary conditions change, they navigate the energetic landscape. They seek alternative closure arrangements that are accessible and dynamically admissible according to the ledger.
And how does this apply to our perfect hexagon, benzene? Because I know from chemistry class that benzene does react. It just reacts differently than normal double bonds.
It perfectly explains benzene's unique, notoriously stubborn behavior.
Stubborn.
Very. It explains it through the principles of closure economy and closure preservation.
Closure economy.
Because benzene has achieved this highly lucrative, highly stable, distributed cyclic closure, it is fiercely economically motivated to preserve it.
It wants to protect the halo.
Exactly. Imagine an addition reaction.
That's an addition reaction.
This is where you force a molecule to break one of its carbon-carbon bonds so you can wedge a new atom into the structure.
Like prying it open.
Yes. If you try to force an addition reaction onto benzene, the molecule resists it with immense energetic pushback.
Why?
Because doing so would sever the halo. It would destroy the global cyclic closure, incurring a massive, insurmountable penalty in the admissibility functional.
Right. It would ruin the perfect symmetry that it works so hard to achieve. It would break the halo, and the ledger would go deeply into the red.
Exactly. So instead of allowing addition, benzene vastly prefers substitution reactions.
Substitution.
Under the right conditions, it will allow you to pluck off one of the peripheral hydrogen atoms sitting on the outside of the ring.
The ones on the edge.
Right. And you can substitute it for something else, like a chlorine atom or a methyl group.
Okay.
This temporarily perturbs the system, yes, but it allows the primary carbon ring, the foundation of the halo, to remain completely intact.
Oh, wow.
It ultimately preserves and quickly restores that highly lucrative distributed cyclic closure game.
So it's protecting its core asset.
The reactivity of the molecule, what it will and will not do in a beaker, is entirely governed by its inherent drive to preserve its specific closure regime.
It sounds like Lillian is rescuing chemistry from being viewed merely as applied physics.
He really is trying to emancipate the field.
By framing chemical reactions as these complex entities navigating this closure space to preserve their architecture, he is giving chemistry its own undeniable independent layer of reality.
Yes.
It isn't just about subatomic particles blindly following quantum equations. It is about these complex, macroscopic, structured regimes actively fighting to maintain their organization.
That is the ultimate philosophical payload of the entire monograph, a concept Lillian calls grounded autonomy.
Grounded autonomy.
Chemistry is undeniably and forever grounded in quantum physics.
Of course.
The subatomic particles, the wave functions, the energetic realities, those are the unquestionable foundation.
The building materials.
But the structural laws of chemistry, the specific ways these macroscopic closure regimes organize, negotiate, and behave, are irreducible to those subatomic parts.
It's like saying you can't understand the breathtaking architecture of a Gothic cathedral just by looking at the chemical composition of the limestone blocks it's built from.
That is a perfect analogy.
The blocks matter, obviously, but the architecture has its own rules.
Precisely. And Lillian maps out a grand unifying hierarchy to make peace between the scientific disciplines.
How does he unify them?
Well, classical chemistry, the Lewis structures, the lines, the letters, the physical models, is the operational grammar.
The grammar.
It is the language we use to talk about and manipulate materials in the laboratory.
Right.
Quantum chemistry is the microphysical formalism. It provides the exact mathematics running underneath the floorboards.
The physics engine.
Right. But closure chemistry provides the structural ontology.
The reality of the structure.
It tells us what is actually organized, what is actually real in the physical 3D space between the atoms.
Wow.
It tells us that functional groups, like an alcohol group or an amine group, are not just arbitrary collections of atoms, but portable closure modules that carry their structural spatial logic with them as they navigate from molecule to molecule.
Man, this has been an incredibly deep, sometimes challenging, but absolutely fascinating journey.
It's a lot to process, for sure.
We have completely dismantled the way we visualize the microscopic world today.
We really tore it down to the studs.
We did. We started by breaking the comforting plastic Lego bricks of our high school chemistry sets.
Rest in peace, ball and stick models.
Right. We moved from viewing the molecular world as a box of static finished parts to seeing it as a dynamic, deeply negotiated series of closure regimes where atoms actively adapt to each other.
A living puzzle.
We learned the great reversal, that physical geometry is the answer to a spatial ledger, not the byproduct of invisible mixing orbitals.
The map is not the territory.
Exactly. We visualized how man-spreading lone pairs compress angles to give us water and ultimately life.
A vital manspreader.
We saw how double bonds or suspension cables layered over a primary scaffold, giving molecules their physical rigidity.
So we can see light.
Yes. And we learned that the mysterious, shape-shifting resonance of benzene is nothing more than our 2D human language failing to comprehend the majestic global halo of distributed stability.
Beautifully summarized. The shift from reduction by aggregation to the primacy of achieved closure organization is, more than just a theory.
What is it then?
It is a conceptual tool that clarifies anomalies that have haunted chemistry instruction and philosophy for decades. It gives physical, tangible meaning back to the spatial reality of matter.
I really want to encourage you, the listener, to take a moment and look at the physical objects around you differently today.
Just look around the room.
Look at the steering wheel in your hands, the coffee cup on your desk, the wood grain of your floor, the very air you are breathing in and out.
It's all doing this.
Everything you touch, everything you see, is not a random, static collection of sticky spheres.
No.
It is a materialized, living solution to an invisible, ongoing spatial negotiation. It is a universe composed entirely of perfectly balanced, breathtakingly complex closure regimes.
It's a beautiful way to look at the world.
And as we wrap up this deep dive, I want to leave you with a lingering, provocative thought to mull over.
Oh, I love these.
If Philip Lillian is right, and the absolute best way to understand molecular physical reality is not by isolating its smallest, most fundamental parts, but by looking at the achieved regime of closure of the whole.
Okay.
What other complex systems in our daily lives are we getting completely wrong?
Oh, that's a big question.
Think about our biology, our complex social networks, our sprawling technologies, our global economies.
Right.
Are we fundamentally misunderstanding how the world works because we are obsessively breaking everything down into isolated individual parts?
Instead of looking at the whole.
Exactly. What if we step back and looked at the negotiated, achieved closure of the whole system? It might just change everything.